Hi everyone, I'm Kaizheng Wang, a junior PhD student researcher from Department of Computer Science M Group, Campus Brugge, KU Leuven in Belgium. I work together with Dr. Kiwan Sharitamanda, Professor David Mons, and Professor Hans Hali. Today, I would like to introduce my literature study with a title, A Study on Epistemic Uncertainty and Bayesian Neural Networks. I will do the presentation as following structure. First is the introduction. Second, the basic concept of the epistemic uncertainty in neural networks. Third, I will introduce the state-of-art method Bayesian neural networks. And then I will introduce the achievements and challenges of Bayesian neural networks. Finally, I will list all the references used in this presentation. Recently, neural networks have made significant contributions to a wide range of scientific fields, but a well-trained neural network may be overconfident in its predictions or even fail in some cases. For instance, in this figure, for the new test images that the neural network hasn't seen previously, the neural network will provide the overconfident and wrong predictions. That means the neural network is still not able to provide robust decisions or predictions based on gathered data and dealing with the uncertain domain knowledge. Therefore, tackling the problem, neural networks and their uncertainties is highly required for researchers. Then there is the motivation I do the literature research about epistemic uncertainty and the neural networks. Epistemic uncertainty is the most important uncertainty in this field. The first question may be, what's the epistemic uncertainty in neural networks? The objective of neural networks in supervised learning is to find a model that can map from the input space to output space correctly based on training data. Out of interest, the expected model should be a right one that can truly minimize the risk. The true risk is usually defined as expected risk. The expected risk is the integral of loss function over input space x and output space y. The loss function depends on hx predictions and the labels y. But in reality, we cannot calculate the integral over the whole space because there are limited training data to be observed. So instead of using the expected risk, we normally use the empirical risk that calculate the average loss over the n observations. So the estimated model after training is actually the empirical risk minimizer. So the result is that after training, we are uncertain about the right model we expect, and we are also uncertain about the differences between the estimated model and the right model we expect. But we can imagine that if n goes to infinite, we can definitely state that the estimated model is equal to the expected model. In such cases, epistemic uncertainty is used to express the ignorance caused by a lack of knowledge, information, and data, and to express the uncertainty between the estimated model and the expected model. In order to handle the epistemic uncertainty issues, the basic idea is instead of creating one specific model, we want to generate a set of reasonable models that could be the candidates of the unknown right model. For instance, in this figure 2, we have a linear regression problem. And initially, we only have 100 training data x, y, and we want to get the function of y regarding x from the training data. If we don't consider the epistemic uncertainty shown in figure A, we can only output one specific model after training, even there are other potential functions between x and y. So we need to consider the epistemic uncertainty. When considering the epistemic uncertainty, we can output several models to express the uncertain about the right one shown in subfigure B. And furthermore, if we can observe more data, like in subfigure C, we observe 1,000 training data. So we can find that the output the models will be more close to each other. That means the more data we observe, the less epistemic uncertain they are. And technically, we generally model the epistemic uncertainty in neural networks by model the ignorance of model parameters. Bayesian neural network is a well-established and widely used approach to epistemic uncertainty in neural networks. And in Bayesian neural networks, the model parameters are represented by probability distributions, like shown in this figure. And normally, Gaussian distributions are widely used. The basic idea of Bayesian neural network is that first we assign a prior distributions over the parameters, and the objective of training a Bayesian neural network is to find the posterior distributions based on the training data. The posterior distributions can be formulated by using Bayesian rule in this formula. W is the parameters. X and Y are training input data and labeled data from the input space and output space respectively. After training a Bayesian neural network, we can get the posterior distribution, and then we can do the prediction. For prediction, Monte Carlo approximation can be widely used. For example, we sample the Bayesian neural network n times, and for each sampling, we can generate a specific model, because for each sampling, we can get specific value for each parameter from the distributions. And then we can average the unoutputted predictions to generate a single point prediction by hat by using this formula. And finally, we can also calculate the covariance of the y hat by using this formula. And the larger the covariance is, the more uncertain about the differences between the prediction and the ground truths. Bayesian neural networks have made tremendous achievements already. For instance, it is confirmed that Bayesian neural networks can outperform standard training and deep ensembles in terms of both uncertainty calibration and predictive accuracy. It is also demonstrated that Bayesian neural networks could discriminate between easy-to-classify test images with lower entropy and difficult-to-classify images with higher entropy in vision classification tasks. Bayesian neural networks are also widely applied in other fields, recently like structure, health monitoring, and cost-informed decision-making, uncertainty quantification in biomedical image segmentation, as well as prediction and classification of thermal preferences. Although tremendous efforts have been made, Bayesian neural networks still have to face challenges. Bayesian neural networks have been criticized for their reliance on prior knowledge. Indeed, gaining insight into the prior distribution of parameters before training a model is extremely difficult. So one of the research direction is to find the plausible priors for Bayesian neural networks. Recently, there are some progresses, but not enough. Weight space priors could be one of the choice. Strongly spatially correlated Gaussian or Gumbel function priors are recently proposed in the specific case of a convolutional neural network for vision tasks. Another choice could be function space priors, for instance, noise contrastive priors, which are specified in functional space directly through a prior over the ANSI data. The second challenge is that in Bayesian neural network, Bayesian rule is easy to formulate but hard to infer. Therefore, we need proper approximation methods. I summarize the pros and cons of the existing method. The methods are variational inference, Laplace approximation, sampling approaches in this table. Currently, Bayesian approximation inference remains an exciting research area. For instance, new accurate and scalable approximation inference methods to overcome the high conditionality and non-convexity of parameter distributions and to balance the optimality and traceability are still under investigation. The next challenge of Bayesian neural networks is that Bayesian neural networks are expected to handle domain shift problems to improve robust predictions in practical scenarios. The domain shift problem is that the training distribution differs from the testing distribution. Recent study shows that Bayesian neural networks have poor generalization capability and the domain shift. The result is based on the use of full batch Hamilton Monte Carlo methods on modern architectures. It is also shown that Bayesian neural networks are only slightly better than models that don't consider epistemic uncertainty for output distribution detection in low-dimensional issues. Therefore, more research on this subject is still recommended. Most recently, a study shows that another method to improve the detection performance of out-of-distribution image classification, language classification, and malware detection tasks, but this method is currently limited in job-out Bayesian neural networks. The last part of my presentation is the references. So thanks for your attention and looking forward to your suggestions, feedback, and discussion. Thank you.